Can everybody hear me okay?
Yes.
Okay, all right, good. Thank you. Just 1 second. All right. So what I want to do today is talk about our second to last lab. We only have two labs left this semester. Okay. These are some of the reminders. So this is the lab I'll be talking about today. Excuse me. And just in case, I did put the due date of our last lab. Actually, I made the due date of the last lab after the final. So you can, not the final, but the last exam. So that at least you focus on the last exam before the lab. I'm hoping you guys are doing okay on the lab, getting it done. I've seen tons of questions regarding the lab, especially in the Discord. And I hope that most of you are almost done with it. Okay. If you have some equipment issues regarding this lab, I mean, I can't get any equipment for you today just because I have too many classes and I have to run the campus to get you the equipment. But if I can get you something in the afternoon tomorrow, I know it's kind of late, but if you need more wire or something, I'd have to do it tomorrow afternoon. Okay, just because of my schedule. The last lab of the semester, I will start talking about it next week. It is a very long, very tedious lab. Okay. This one, you got to get started right away. There's a tremendous amount of data you're going to collect and a tremendous amount of analysis. It's not as much as the version we do when we're on campus. Okay. But just realize this is a very long lab. And if you wait till the last minute to do this lab, you'll never get it done. Okay. So just realize this. So I don't know, those of you if you took 215 and you did a driven damped harmonic oscillator lab, this is just as long. Okay. All right. So the transient, let's talk about the new, I want to talk about the new lab today. Just a few comments before I get to this. Graded the scope lab. You got my email regarding it. And really, I thought there was too many people who just showed how to make the measure, just showed how you use the scope. I mean, just showed how you get the signal on the scope. If you just show somebody how you get the signal on the scope, but then don't show the people how you get the measurement from it, that's not enough. Okay, I mean, you also need to show how you get the information from it, because the lab says show me how to use a scope. It's not just showing how you get a signal, but it's also extracting the information. So talk about that. I had some videos where the student didn't say anything and just showed the signal and that was it. What do you say something. Okay? You want to explain what you're doing. So this semester, I mean last semester when this lab was done, everybody showed how to get the signal and how to extract the information from the scope. So I don't know what happened this semester. The same lab. Okay. Also for the DC circuit analysis lab, and I apologize, my goal was to finish grading that yesterday, but things come up and I get pulled away. I did grade the other lab sections, DC circuit analysis lab, but I didn't grade yours. And I will send comments to you regarding that lab. But one of the things I've noticed, and this is based on what I graded the other group, is when you're asked the question, do two values agree? And still, students are focusing on the percent error. Still, students are being subjective and not objective. If you have two measurements, whether these two measurements agree or not has to do with the range of values they span. When you measure something, you're not measuring a single number, you are getting a range of values. It's not a number, but a range of values. Okay? And it is hard to unlearn that because probably in high school what you learned is you get a number and that's it. But in reality, what you're doing is you're getting a number along with this uncertainty, and so your value represents a range. If these two ranges overlap, not the uncertainties, but if the range of these two values overlap, then they agree. If they don't overlap, then you probably have a systematic error. And that's based on how we assess these uncertainties, right? Because in this class, our uncertainties are only based on random errors. Okay, so that question will be asked of you a lot this course. The next two labs will be asked of you, and it will be asked of you in 215. And you got to answer the question objectively. Okay, you have to be objective. Don't say, oh, it's close, they're close. What does that mean? What does close mean? How do you define close? That's subjective. And in science, especially nowadays, with our political climate, you really need to be objective and not subjective. Okay, as much as possible. Yeah, so Kai, isn't it true that when we assess our uncertainty, except for the multimeter, when we assess our uncertainties, they're based on random error, right?
Yeah.
And so we're not assessing the systematic error, right? Except for the uncertainties, except for the multimeter, I'm sorry. So if the values don't agree, isn't it possible that, or isn't it likely that there is a systematic error in one of these two measurements? For example, I'm forgetting the resistance of the multimeter in the experiment, right? The fact that I'm not including the resistance of the multimeter in these calculations, I mean, is that a systematic error? And that's basically what's really what I'm saying. All I'm saying is that if they don't agree, that it's indicative of the fact that there's a systematic error. I'm not saying it is, but it's indicative. Okay, I don't want to be definite. Okay. All right. So that's been an issue, and this is going to be asked over and over again. And so we're trying to force you into giving an objective as objective an answer as possible. Okay. So that's what I'm looking for. And when you take 215 from Harris, he's going to expect the same thing. Okay. As you get into 210 and 215, this question is very important. Okay. But when you say the two values are close, because I had a lot of people say that, that's very subjective. And we're just trying to force this kind of thinking on you as opposed to subjective. And like I said, this is very important in today's political climate. Okay. Yeah, I think the other thing too that I noticed is when people did the calculation on the last part, a lot of people did it exactly the same way, and they didn't even simplify it. They had a horrendously complicated equation. I had a huge number of students do it exactly the same way using Kirchhoff's law. They had the same final equation that was very complicated. If you didn't use Kirchhoff's laws and just use the rules for series and parallel, you get the answer right away. But anyway, it's interesting to note that. Okay, let's talk about the second to last lab of the semester. It's due May 10th. I don't think it's that long a lab, I tried not to make it a long lab. There's a couple calculations that might seem a little long, and I'm going to go through one of them just so that you understand how to do the calculation. Okay? So let's start. There's 3 parts to the lab, and I'm going to spend the most amount of time talking about the first part because the second part, a lot of the stuff I say about the first part will apply to the second part. Okay? So we want to look at the RC circuit. And yeah, you have to go back and remember the material that you learned about the RC circuit. The reason why I saved it to here is because this is where you've learned how to use a scope. And you need to use the scope to be able to analyze the RC circuit. Just remember that the scope is the most important tool you'll be learning in this course in terms of analyzing circuits. The scope is way more useful than the multimeter. Okay, so let me draw the RC circuit. We're going to be using a square pulse to analyze the RC circuit because we're going to be looking at the voltage across the capacitor with a scope. If I use a battery, the capacitor will charge up and then you'll just get a horizontal line on your scope, which is boring. We'll have a resistor, which is 100 ohms, our capacitor, 4.7 microfarads. That's our circuit. And you can build it on the circuit board, the little proto board, okay? So you can build it on a proto board and then connect your circuit to your signal generator. Now, when we talked about RC circuits, we derived the expression for the charge on the capacitor. I applied Kirchhoff's law, solved the differential equation, and came out an equation for Q. And if you take the Q and divide it by the capacitor value, you will get the voltage across the capacitor. And it looks like this. So you're going to have to review this. You're going to have to review where this comes from. Okay? And you might need to know about how the capacitor works on the last exam. Because we're going to be dealing with resistors, capacitors, and inductors in the last unit. So you do have to know this equation still. Okay? Okay, so this is going to be our working equation. And what we're going to do is we're going to look at the voltage across the capacitor on the scope. So you're going to put a square pulse in. I was going to draw it like this. When in reality it goes positive and negative. These are supposed to be the same distance. That's bad. So if this is your signal generator voltage, your capacitor will do something like this. These are supposed to be equal. I just did a poor job drawing, sorry. Okay, your capacitor will be charging and discharging. So you're going to be looking at this signal. Actually, what you need to do, and this is one of the unfortunate things about what we have for the equipment. Your scope only allows you to see one signal at a time. So you're going to have to first look at the signal from the generator by hooking up the scope across the generator, and then you're going to connect the scope across the capacitor to get this red one. Okay? You're going to have to do it, you're going to have to go between the two all the time. Okay? You need to look at the signal generator to make sure that this voltage is correct. You're going to set this to 1 volt. The amplitude's got to be 1 volt. The peak-to-peak voltage has got to be 1 volt. Okay? So this will be 1 volt. Somebody asked me in the previous class, why did you choose 1 volt? Well, number one, choosing that number is arbitrary, but in our particular case, that 1 volt is important because the signal generator is current limited. If I put too much current in it, it's going to really mess everything up. Okay, but in reality, if you have a good signal generator, the voltage that you need to do this experiment, it doesn't matter. Okay. What we're going to do is we want to try to verify this equation. We want to better understand how to analyze this circuit and become more comfortable using this scope by measuring, by basically calculating this value from this equation. Okay, we're going to calculate the value of C from this equation and compare to the measured value with the multimeter. So like I said, we're going to learn how to analyze the circuit and become more familiar with the scope in this lab. So how am I going to verify this? Okay. We're going to make a simple measurement. I'll say that I'll tell you about that in a minute. And from it, we'll be able to calculate C. But before I talk about how we get the value of C, I need to say some very important things about this circuit and the scope. And this is described in the video that Tyler made for you for this lab. And I sent you the link to the video in an email last night. You got to watch it. So the scope is grounded. One of the inputs on the scope is grounded, but it's on our particular one, it's not an earth ground, but it's a common ground for your circuit. Okay? So one terminal is always a ground. Okay? So one terminal always connects to the negative side of your signal generator. That means that if you're going to use the scope to measure the voltage across one of these elements, that element has to have one of its ends tied to ground. This is why I have the capacitor second. If I put the scope here, what would happen? The current would go through the resistor and then to ground. It would completely bypass this. And if you were working with transformers doing this, and you did it wrong, you would get a severe shock. So it's an important safety tip to make sure you understand that whatever you're measuring has to be grounded. One side has to be grounded. So the one side of this capacitor goes to the negative side. So this is negative, this is plus. This has to be tied to the negative side, just like this. Okay, that's important, and in the video, Tyler talks about that. There is no way now, the way this is set up, to measure the voltage across this. The only thing you'd have to do is swap the positions of these two in the circuit in order for you to measure the voltage across the resistor. Okay, that's important. Make sure you understand that when you do this lab. Okay, otherwise your results are going to be terrible. You're not going to see anything. It's going to be terrible. Okay, that's important. So, having said that, how are we going to be able to get C from the scope? What we're going to do is the following. Let's take a look. Let's assume this is the scope signal for the capacitor. This is the capacitor voltage as a function of time. So this is time. I guess I should use black. This is voltage. Okay? And this is the scope trace. This is not a graph. On a scope, they call it the scope trace. And what you're going to do is find the time it takes for the capacitor to be charged to 1/2 its maximum value. In other words, you want to find when delta V sub C over the battery voltage is 1/2. In our particular case, since the peak-to-peak voltage is, since this voltage is going to be 1 volt, you want this to be half. You want it to be charged to half the maximum value. Does that make sense? So you want this ratio to be 1/2. Well, if the ratio is 1/2, let's take a look at this equation. Let's divide both sides by V. I want to solve for C. So this is 1/2. I'm going to do 2 steps at once. By the way, make sure you take notes here because you have to derive this equation. If you send me an email about how you derive the equation, I'm going to say watch the video. Okay? So I'm going to do 2 steps at once and I'm going to get the following. Then I'm going to take the log of both sides. Now I want to get rid of the minus sign, so I'm going to do a trick with logarithms. So then C is T1/2 over R, natural log of 2. So this is going to be the calculated value of the capacitance. Okay? That's going to be the calculated value of the capacitance. What's R? Can anybody tell me what R is? What should I put in?
From our last lab?
I'm sorry?
Is it from our last lab?
That's part of it, right?
Just the 100 ohms?
Yeah, so it's going to be this value plus, because we measured, this thing has a resistance, right? You saw that.
Yeah.
So this resistance plus this resistance is R. So this is really like an equivalent resistance, right? Or a total. Maybe we'll call it R total. So R total, and you got to measure that, right? It's not exactly 100 ohms. It's going to be 100 ohms plus a signal generator, and it's the value at the frequency at which you measured it. You did this already, right? So one of the issues that happened was that some people at the lower frequencies got a value that I thought was too small, but it's possible that there are different versions. I mean, you might have a different version of the signal generator than I do. When you turn it on, there's a word that pops out. Mine starts with the letter X. It's like Ximen or something. But the previous version that I had a different name on it. So it's possible that there's a component that's a little bit different in this supply. These are cheapy supplies, okay? I want to show you the difference between this signal generator and a good one. Yeah, okay, there was a lot of people who got a value that was lower than I thought. So I don't know. You know, all I said on the lab is this looks low, and that's all I can say because I don't know about the quality of this thing. And you're going to see, I want to show you that this signal generator is not high quality. And it's going to be one of the issues we might be dealing with. It's especially important in the next lab. Not this one. The next lab, this signal generator becomes problematic. Okay? And I've done everything I can to reduce the problems as much as possible. Okay? Part of it is it can't drive a lot of current. Okay? So I actually have 2 signal generators. I'm going to show you the difference between the two in a little bit. Okay? So this is our total. So, okay, so it's this plus this. Okay. So you're going to obtain C from this equation by making this measurement. You're going to do it at 3 different frequencies. You're going to also calculate the uncertainty in this value for all these frequencies. Okay. In part 2, you're going to replace this with an inductor, but you're only going to do it once. And the reason why I want you to do it at 3 frequencies, I just want to notice if maybe there's a trend. What happens as you change the frequency? Okay. By the way, there's other ways to make the measurements with the scope, but this will allow you to do some of the other techniques. So Jacob, the R sub S is the signal generator resistance that you measured last week that's in the table. Right, you created a table last week for the signal generator resistance as a function of frequency. You're going to copy and paste that table into the appendix of the lab. By the way, make sure you use the latest version of the lab that I sent you last night, and I uploaded it onto Canvas. There's a couple, they look like minor changes, but they're actually important changes, okay? All right. So we're going to do this for 3 different frequencies, same capacitor. Not necessarily, Jacob. They weren't necessarily the same. And the reason why is because generally there's a capacitor at the output, and it blocks DC current. So when you're at lower frequencies, you will see the effect of that capacitor, but when you're at higher frequencies, you don't. Okay. So not necessarily the same. In mine, it wasn't. It went from like 80 down to, and it asymptotically approached 50, because it says in the manual it's 50, but it's not exactly 50. 50 is really the asymptotic value. Okay, and that's an approximate value. All right, so we need to talk about how we get the uncertainty in the calculated value, because I know this will cause a little bit of trouble. And what I say here will also apply to the inductor. So I'm saying that now because I want you to understand that what I'm going to do for the capacitor will also apply to the inductor, because you got to do the same thing. Okay, so this calculated value involves 4 measurements. Do you see that? This equation involves 4 measurements. What are they? Anybody want to guess what they are? Actually, it involves more, but actually, if I want to do it,
the voltages, or
yeah, there's 2 voltages, right?
yeah, but are you counting both of the resistors? Because now I'm confused, because that would be 5, right?
Yeah, you're right. That's 5. That's my mistake. You know what? I'm going to count this as. And you'll see, I'm going to even count this as 1. You'll see what I'm going to do in a minute. But yeah, there's 5. But you know what you can do is you can always calculate this ahead of time, right?
Yeah.
Right, because this is going to be. But you're absolutely right. There's really 5 in there. Okay, but I'm counting this as 1, and then what I'm going to do is make this look like it's 1 also. Right, because this is really, it's the reciprocal of this thing. Right, it's going to be, this is 2, but this 2 is a measured number. It's not an exact number, right? And yeah, I should probably put our total here. And in the lab, it actually has you figure out what our total is, right? So then how do I find the uncertainty in this? I can't just, how am I gonna write this? It's just weird. So I'm gonna do the following. Let's let A equals so now it looks like I only have 3 measurements here, right? I know the uncertainty in this, I know the uncertainty in this, and I know I'll figure out the uncertainty in this in a second. Am I frozen?
Yeah, I believe you are.
Okay, my camera, my other camera is not. Boy, I don't want to quit the video. Hold on a second. I just don't want to quit the Zoom. Restart it. I'm going to try something real quick.
Recording stopped. Recording in progress.
How about now? Is that better?
Yep, we can see you.
Okay, good. All I did was I turned the camera off and I turned it on. That's weird. Okay. So we're okay now, right? So here, what I did is I let this be A. Yeah, it's weird. This little things you can do. I didn't want to shut off Zoom. I didn't want to restart. That would have been bad. So I got lucky. So so A is delta V over delta C, which is supposed to be 2, right, in principle. You're measuring it to be 2, but I want to be able to assess the uncertainty in this. Okay, so my goal is to get the uncertainty in C, but before I go on, how am I going to get the uncertainty in A? The uncertainty in our total is this thing. Okay, so I know delta R total. I'm going to call this R1. So I'm just going to count this as one entity for now. Okay, I'm going to erase the board because I'm going to do some math here. So I want to calculate delta A. So delta A is going to be the partial of A with respect to, and I hate this notation, and then the partial of A there's 2 deltas. I don't like that notation. That's why you'll probably see people drop this delta, the first delta, okay. Yeah, it's error propagation. Okay, so I'm not going to go through the steps, but it ends up being this. Oops. Too many deltas. But of course, this is just 2.
Wait, I thought it wasn't actually 2 though, because we're measuring it. So it's going to be like near 2, but not actually
It's near
2.
2, right? 2.0. I mean, you're supposed to do it. You're supposed to get 2, right? I mean, because you're measuring the time at which this is a half,
Yeah, okay.
right? I mean, in principle, it's 2, but of course, there's an uncertainty associated. That's what we're calculating. I mean, it could be 2.0 or whatever this comes out to be. Whatever that number is. Okay? And that's
Okay.
based on the resolution of your scope, which is you're not going to get better in one decimal place. So that's what delta A is. Now, what's delta C? Well, I guess error propagation. This is fun. I'm going to take the derivative of C with respect to t1 half plus the derivative of C with respect to R total plus the derivative of C with respect to A I think doing it this way is a lot easier than having 5 terms in partial derivatives, right? Don't you think so? This is a lot easier than to just write this out in gory details and then, I mean, try to take the partial derivative of this thing with respect to V sub C. You'd have to be using, I don't know how many differentiation rules to do that. I would probably make a mistake. So instead, I'm doing it this way. I'm less likely, at least I am, less likely to make a mistake. Some of you folks are probably really good at doing this, so you might not make the mistake, but I would. So what happens now? Let's do the calculation. This first term is easy, right? If I take the derivative with respect to t1 half, I'm going to get actually, I should have pointed to this one. And remember, A is, in theory, I mean, in principle, A is supposed to be 2, right? The second term is going to give me, and I'm not going to be worried about signs, and I'll let you try to figure out why. And here's the last term. You want to check my algebra. Looks like that. Look okay to you folks? You're going to do the same thing when you do part 2. So I'm only doing it once, and you should be able to figure out how to do the other one. Okay, and the reason why I got these 2 terms is because I'm taking the derivative of 1 over natural log of A, which is always fun to do. Okay, What am I missing in this term and this term? What have I ignored?
The negative, but squaring it doesn't matter.
Yeah, because it's squared. So Kai, you need to show the equation for the other one, because the other equation is going to look a little bit different. The value for the inductance has the R up here. Okay, so it's going to be the form of the equation for the inductance has the resistance in the numerator. And so yeah, you're going to have to do it both times. I mean, you're going to do the capacitor, you're going to do 3 times, but you're only going to do this once, right? Just show it once. But then for the inductor, you'll do it once also, but the equation will look different for the inductor. Okay, but this part will, this issue with the natural log of A is the same. Okay, right? That's the reason why I'm going through this, but because L is going to look like this. I'll derive it. Or I'll put A, whatever. It'll look like that for part 2. Okay? This one? Jacob, are you talking about this term? It's R total times A times the natural log of A squared. So it looks like this last term is like this. You should verify it though when you do this, okay? Verify that I did the calculus correctly. But yeah, I want you to do it, and then you'll do it for the inductor. So it's a little bit messy. Yeah, it's probably a little bit blurry when the camera can't focus on it. The camera's I'm forcing the camera to focus on too big of a region. Are we okay? All right. No, any other questions regarding this? You'll be doing it for 3 frequencies. And I did forget, and I will bring up an issue in lecture today. I forgot to talk about how you get this, and I forgot to tell the other group how to get these values from the scope. So in lecture today at the beginning, I'll mention that. Okay? Okay. So what I'm going to do now is I want to show you the circuit. So I'm going to unplug my microphone, plug in my other camera. Okay, let me just focus on that. And by the way, I always forget, sometimes I'll go to the board from here and I'll forget to switch cameras. So just remind me, just blurt it out. Okay. So one of the things with the capacitor in this lab, you can actually physically measure the capacitance of a capacitor directly. In your, with the multimeter, you have, and then the big multimeter has one of these. Okay? It has one of these in it. And so I have a random capacitor. This is a capacitor. Okay? It's a random one. And I'll show you the capacitor we're going to be using in the lab. And I probably shouldn't grab this one because the leads are giant. And you're going to stick the capacitor in like this into the little gray thing. This is used to measure capacitance. Although you don't need this to measure the capacitance. You can always use the alligator clips. And let me find my multimeter. Here's my big multimeter. Okay. And you use these sets of leads to measure capacitance. So you stick this in, like so. And this capacitor is different from yours. So this one's 0.47 microfarads. So you can measure it directly with the multimeter. Okay? And then if you read the manual, it'll tell you what the uncertainty is. Okay? Are we okay with that? So you can actually measure it. Yeah, I mean, hold on a second. Let me double check that. It doesn't say so. It's basically for capacitors and transistors. You can measure the characteristics of the transistors with this. Now, there's an L on there for inductors, but the multimeter, I mean, this multimeter does not measure inductance. Okay? I think they probably have a different version of this that costs like double or triple that measures the inductance. It's amazing that just to measure inductance, it doubles or triples the price of this thing. Okay, so the capacitor you'll be using, I got to be careful because I'm going to mess up my circuit. You see the, this is the capacitor right there. That's what it looks like. Can you all see that? Okay, that's the capacitor to be using. Okay, it's polarized. And it says 4.7 on it. Okay. And I have it hooked up, and I have it hooked up to my scope. My scope shows you the input and the output. So the yellow trace that you see is the voltage from the signal generator. Does anything bother you about that? Is that a square wave? Not really, right? It doesn't. It's distorted, right? Yeah, it's kind of distorted. I think it has to do with the capacitor at the output. And then the orange one is the output from, or the voltage across the capacitor. And what you want to do is, you want to spread. I'm having triggering problems. Yeah. You want to spread the signal as much as possible vertically and horizontally so that you can measure accurately T1 half and V1 half. V over V, V over V sub C over V to be 1/2. Right? The bigger you make the trace, the more accurate you'll be. Okay? So that's what it looks like. Of course, you're only going to see one at a time. By the way, you should realize that every time you change the frequency, the signal generator voltage will change. It might not be 1 volt. So every time you change frequency, you got to guarantee that the voltage, the amplitude is 1 volt. You got to measure it. Okay. So now I'm going to show you what happens when you use a good one. Okay. So I'm going to switch. Now the good one is, the good signal generator is hard to see. It's back here. It has a blue face and a blue screen on it. That one costs about $500 as opposed to the $30 one we have. So we couldn't afford to have each student get a $500 signal generator. So let me get the negative connected. Let me turn up the voltage. You notice the difference? Hold on a second. You see the difference? It actually looks like a square. Actually, there is no true square pulse because a square pulse is really a linear combination of sine functions of different frequencies. It's an infinite sum, or close to infinite sum as you can get. But look at that. And the rise time almost looks like it's 0, but it's not. If I had a good scope, I can measure the rise time. That reflects the difference in the quality of the signal generators. Okay, so the signal generators will be an issue in these last 2 labs. Okay, that's what it should look like. And part of the problem with the signal generator, if it's because it's connected to the circuit. If you actually just remove it from the circuit and just hook it up directly to the scope, the signal generator will look pretty square. Not as good as that one. Okay, it won't look as good as that one. But it'll look much better if it's not in the circuit. Because you're loading the generator, the signal gets distorted. Okay, it's not a very powerful signal generator because it can only handle low currents. But the other one can't. It can handle much higher currents, and so that's why this is very square. Okay, I just wanted to show you a comparison between a good one and a not so good one. You can't see it, but it's back here. The signal generator. I have too much stuff there. There's rods in the way, etc. Okay. I'm worried about moving the rod and everything falls down. Oh, are we okay with that? Okay. So now let's talk about the second part of the lab. The second part of the lab is really very similar to the first part of the lab. The uncertainty analysis is very similar. The only thing is the equation is going to look like this. So I want to talk about this. Okay. In the second part of the lab, you're going to replace the capacitor with an inductor. So let me draw the circuit. And the analysis will be a little bit different. Now, what's an inductor? In lecture today, we're going to talk about an inductor. We're going to start in chapter 32, and I'll talk about inductance. Basically, it's a coil. Okay, that's all an inductor is basically a coil. So we'll have our signal generator, square pulse.
Can you change your microphone,
Oh, sorry about that.
please?
It sounds that bad, huh? Okay. Hold on a second. Nope, not that one. Is that better?
Yes, way better.
Okay, sorry. All right. We have a coil called an inductor. We're going to put it here. Its nominal value is 10 millihenries. Okay, I want to make sure you guys can see that, okay? And then we'll have a resistor here. And I put the resistor here, and we're going to measure the voltage across the resistor. The reason why is actually it's easier for you guys to do the analysis. It's easier for you guys to find T1/2 with the resistor as opposed to the inductor. Because with the inductor, it just drops off too fast. Okay? So if you got the latest version of the lab last night, the circuit will look like this, and then you're going to put the scope across the inductor. And remember, one end of the resistor is going to be tied to ground. And by the way, this is 47 ohms. I'll call it R1. So this is just a big coil. An inductor is just a big coil. An inductor is a device that opposes a change in current. The voltage across the inductor, and I'm going to show this in class today, at least the magnitude of it, all right, is L di over dt. I should do that to be precise. Okay? And I'll show where this comes from in a lecture today. Using this term here and I times R here, applying Kirchhoff's laws, you can show that the voltage across the inductor, you can solve for the voltage across the inductor and get the following, where delta V is the power supply voltage. L is called the inductance. Again, we'll talk about it in a lecture today. Okay? And the voltage across the resistor is basically the power supply voltage minus this is going to be this, following. You see inductors in cars. If you work on cars, I don't work on cars, but you see inductors in cars. The coils. Okay. And in motors. Oops. So what you're going to do is you're going to look at the voltage across the resistor, and you're going to determine when delta V sub R over delta V is equal to 1/2. And let's call that time T1/2. Okay? And from that, you can derive the equation for L. So let's do that. And again, this is going to be in your theory section of your lab report. Okay, so I'm going to set this, I'm going to divide both sides by delta V. And we're going to set it equal to 1/2. I'm going to take the log of both sides. And then I'm going to do that trick where I flip this over. Remember, 2 is delta V over V sub R. And really, this is our total. It's not just a 47 ohms because we have a signal generator, right? So this is our calculated value. You have measurements here, and measurements here. So what's our total in this particular lab, this particular part of the lab? What's our total? Well, it's R1 plus R the signal generator. But there's one more term. Guess where the other term is? Remember, this is it's a coil, right? It's a long wire. Do wires have resistance? Yeah, the answer is yes. So actually this has really 6 measurements, right? 3 for this and 2 for those and 1 for that. Okay, but again, do what I did before with the uncertainties. Right, so delta RT You actually need to measure the resistance of the inductor. And I got to show you what the inductor looks like. So I'll do that in a minute. Okay? Are we okay with that? Same analysis as the other lab, as part, not the other lab, but the first part. Okay? Now, you cannot measure with the multimeter this value. And I can't see the writing very well on the inductor. So we're going to assume its value is this. 10 plus or minus 1 millihenries. Okay? We can't measure it. The multimeter doesn't measure it for us. So you're going to compare this to this. This is the calculated value. And you're going to do the inserting. You're going to see if the values overlap. You're only doing it at one frequency, so you're only doing it once, so it should go quick. You can one day do the capacitor, the next day do the inductor, and then the next day do the last part. Now, the last part of the lab, which I'm just going to tell you what you're going to be doing for now. You're going to put a capacitor in here. You're going to have these three in the circuit. And you got to apply Kirchhoff's laws to see how this circuit responds. And so when you solve this, Kirchhoff's law equation, it's actually a second order differential equation. I will solve it next week. I know this is not Math 33, and Math 33 is not a prereq. But what I'm going to do is use an intuitive method to solve it. I'm going to guess the solution. Okay? Which really is a Math 33 technique, but it's the most intuitive way we can do it. So I'm going to actually guess the solution. I'm going to set up the equation, guess the solution, and see what comes out of it. Okay? And in one of the solutions, if you choose your values of the resistor, the inductor, and the capacitor properly, and you put in a square pulse, you will get something called an underdamped signal. You'll get something called ringing. You'll get a decaying sine function. Let me show you what it'll look like.
You're frozen again.
Again? Okay. Hold on a second. Let's see if I can do this. Make it work again. Okay, good. So I did this, maybe it was last semester. Actually, we didn't do this last semester because we weren't given the correct inductors. So here's, actually, let me make it larger because it's harder to see. So this is called an underdamped circuit. And so what I want you to do is choose a value of R, L, and C in the frequency so that you observe this decaying exponential. It's not a decaying sine function. Okay? The best example is the one on the bottom right. So you might wonder, well, how am I going to choose R, L, and C? So when I solve the differential equation, I'm going to come up with a condition for which this ring, it's called ringing, this effect occurs. Okay? So the one on the bottom right is like the best one, but the top two, the ones in the top row, the first two are okay too. So basically I want you to show an example of these. And you're going to take a picture of the trace of the scope and you're going to measure the frequency of this oscillation. Okay, that's what you're going to do in part 3. That's all you're going to do. But in order for you to do part 3, you need my derivation. So I'll do that next week. So next week I'll talk about part 3 of the lab. And then I'll start the next lab. I need to start the next lab next week. Okay. When I derive the equation next week, I'm going to assume just a DC input. I'm not going to assume a square pulse. Okay. By the way, when you try to observe this, you actually have to expand the scale, because if you squeeze it too much, you won't be able to see all this damping occurring. Okay. I want to show you what the inductor looks like. So again, I'm going to change cameras. Hold on. Connect the microphone, sorry. But I'm close to the computer, so you should still hear me. And why is it working? Okay. All right, so your inductor looks like this. In fact, your kit probably comes with 2 inductors. Okay? The small one is the one you want. The big one is actually 1 millihenry. The small one is 10 millihenries, which is strange. Okay, so you want this one. You see what it looks like? This is the one you want to use. Last semester, we had an inductor. It looked just like a resistor, so it was very confusing. So I asked Tyler to... Sorry, I didn't see the chat. The chat was behind my Excel spreadsheet. The one I had last semester looked just like a resistor, so it's very confusing. So I asked Tyler to get one that's different. And so this one is a little bit more discernible from a resistor. But the writing is very difficult to see on it. In fact, in the 10 millihenry one, there's no writing at all, I don't think. Okay, so I don't know what the precision is of this thing. Of course, if I had the spec sheets, I can tell you, but I don't have the spec sheet. So we're just going to assume it's 10 plus or minus 1 millihenry. Questions or concerns? Let me go back to let's view. No questions, are we okay then? So this lab will be due on May 10th. Okay. Like I said, each part is not very long. It should be straightforward. It was actually last semester when we did it, we really never measured the resistance of not the resistance, but the impedance of the signal generator. So the results were not that good. You guys should get good results. Okay. And I tried to choose resistor values. And I'm kind of pushing the limits right now. I'm pushing the limits of the system because really, if I make a resistor like 1,000 ohms, I wouldn't really have any problems with the signal generator, but the signals would be small, and you might get interference from the outside. Okay, because the signal would be small. So I'm actually kind of pushing the signal generator kind of to the limit in this lab. So I have smaller resistance value. Also, if I had R to be very big, the decaying exponential for the inductor would be very fast. It would be hard to measure. So I chose values to make life easier for us. Okay, if we had a real good signal generator, I could probably choose any values for. In a better scope, I could probably choose any values for R. All right, if you guys don't have any questions, I'm going to end it here. And we'll see you at 2 o'clock.
I actually have a question on, so I saw a comment on my scope lab. I think I fixed the issue with the videos. If you could check that.
Oh, okay. Okay, good. Yeah, because it wasn't playing at all.
Yeah, like for some reason it was playing on my computer, so I sent you like the individual links.
Okay, I'll look at it then.
So if that doesn't work, I still have them on my phone, so I can re-upload them.
Okay, yeah, the first 2 worked, the next 2 didn't.
All right.
All right, okay,
Thank you.
you. Any other questions? Okay, then we'll see it too.